Let's look at a theorem from your book in section 6.3. It says, let A be an n by n matrix with the following characteristic polynomial. P of lambda is equal to this, where each one of these lambda i's is an eigenvalue, and each one of these mi's is an associated algebraic multiplicity. Let's take a vector from each one of the eigenspaces. So let x1 through xk be eigenvectors, where xi belongs to the lambda I eigenspace. So we're taking one vector from each eigenspace. The set of all of these vectors, x1 through xk, because there's k eigenvalues, so we're going to have k eigenvectors, this set is linearly independent. We're going to prove this, and how we're going to prove it is by contradiction. So we're taking vectors from each eigenspace, one vector, and we're going to assume that these vectors are linearly dependent. Well, we can form a linearly independent set from the set of vectors. So if we've got, for example, x1 through x10, we can just get rid of the vectors that are linearly dependent and just form a linearly independent set. So you want to find the biggest possible linearly independent set, and you want to reorder and rename them. You're going to rename them x1 through xr, and this set is going to be linearly independent. So let me go back through that real quick. So let's say that we have the vectors. I'm going to put a little comment here. So let's say you have the vectors x1, x2, x3, x4, x5, and x6. So it's 6 vectors because you have 6 eigenvalues. And let's say this is a linearly dependent set, but let's say that this vector, and this vector, they're linearly independent. And the other ones, if you add x1 to this set, so we have x2, x4, and x6. So if you add x1 or x3 or x5 or all of them, then you would form a linearly dependent set. So what you're going to do is you're going to rename these. This one's going to be x1, this one's x2, and this is x3. And then you're going to call the other 3 x4, x5, and x6. It doesn't matter what order you put them in. But you want to find your biggest linearly independent set. You're going to rename them x1 through xr, depending on how big your set is. And this r has to be less than k, because we're assuming that these vectors, these k vectors, are linearly dependent. So it's going to be a smaller set than what we have. And anything bigger than r is going to be linearly dependent on the vectors before it. Okay? Well, if this set is linearly independent, then we know if we have c1 times x1 plus c2 times x2 all the way to cr times xr, this is equal to 0 if and only if all of these ci's are equal to 0, because they're linearly independent. But if I add an extra vector here, so let's say instead I have c1, x1, c2, x2 all the way to cr, xr, but then I also add cr plus 1, xr plus 1, and set that equal to 0. Because this is a linearly dependent set, because I'm taking a vector outside of the x1 through xr and I'm adding it to it, then cr plus 1, if that's not equal to 0, then some other ci's are not equal to 0 as well, because this is a linearly dependent set. So if I assume this one's not equal to 0, then because this is not the 0 vector, it is an eigenvector. And remember that we said by definition eigenvectors are not the 0 vector. And in order for it to be linearly dependent, at least one of these has to be non-zero. Okay, so if that's true, we're going to consider A applied to this C1x1, C2x2, all the way to CR plus 1, XR plus 1. If you apply A to this, you're going to get C1, well, you can send in the A. And then remember that these are eigenvectors, so you'll get C1 lambda 1 x1 plus C2 lambda 2 x2 Now what I'm going to do, I'm going to keep this in mind, that I have this statement, and remember that I had this statement as well. I'm going to multiply this statement by lambda r plus 1. So I'm going to get a C1 lambda r plus 1, a C2 lambda r plus 1 x2, all the way to CR plus 1 lambda r plus 1 XR plus 1 is equal to 0. And then I'm going to subtract these two equations. So I'm going to put a star here. So I'm going to say multiply that equation star by lambda r plus 1 and subtract star from, let's call this equation, let's call it a dot with a circle. So subtracted from this equation here. So in other words, we're going to have this C1 lambda 1 x1 plus all the way to CR plus 1 lambda r plus 1 x r plus 1 subtract C1 lambda r plus 1 x1 plus all the way to CR plus 1 lambda r plus 1 XR plus 1. If we subtract those two equations, we're going to get 0 because both of the equations are 0. And then you just want to group the coefficients together that go with the right eigenvector. So if you do this, you'll get that C1 times lambda 1 minus lambda r plus 1 x1 plus C2 lambda 2 minus lambda r plus 1 x2 all the way to CR lambda r minus lambda r plus 1 XR. That is equal to 0. Let me make this a little bit smaller so we can see it in the video here all at once. So let's do that. Okay, you can see that this part repeats, and that's why I don't have this going all the way to r plus 1. And you can see that I have this one minus this one. So that's how I got the C1 lambda 1 minus lambda r plus 1. Okay, so we said that these CI's are not all 0. That was our statement up here. In order for this to be true, and we said that the CR plus 1 is not 0, then we had to have some of these not being equal to 0. So those CI's correspond to the CI's here. Okay? But notice that I have a linear combination of x1, x2 all the way to xr, and these are linearly independent. So in order for these not to be, these CI's, if they're not 0, this whole coefficient has to be equal to 0. And that tells us that some lambda I minus lambda r plus 1 is equal to 0, which tells us that there's some lambda I, where I is between 1 and r, is equal to lambda r plus 1. And because of that, we said that these were distinct eigenvalues, and they had distinct eigenvectors, that each one of these eigenvectors are coming from another eigenspace. And since we have shown that if these vectors are linearly dependent, we get that they're coming from the same eigenspace, then we have a contradiction. So they are linearly independent. Okay, from this, what do we know? Now we know, because we chose any vector from the eigenspace, lambda I, and any vector from the eigenspace, lambda j, and we said that these vectors are linearly independent. So you can't get the vector xi. Xi cannot come from the vector xj, from the eigenspace xj. So altogether, what this is telling us is that xi intersection with xj, that is equal to the 0 vector as long as I is not equal to j. So these eigenspaces have nothing in common except the 0 vector. All right, let's move on. Recall that we said two matrices A and B are similar if one of them can be written as the other times an invertible matrix on the back and the inverse of it in the front. And we had a lot of nice properties with similar matrices. One thing is, if you take the determinant of A, then it's just the determinant of B, because you can say that the determinant of A is the determinant of Q inverse, determinant of B, determinant of Q, and these two crossed out. That was one thing you could do with this. You could see that the transpose of this would be Q inverse B transpose Q, and you could also do a lot of calculations with this, particularly if this was like an upper triangular matrix. In this, you wanted to find the determinant of this matrix. Well, if you know what the determinant of an upper triangular matrix is, then you could just multiply it by, that would be it. You just have to take the determinant of this one, which is a lot easier to figure out. It would just be multiplying everything on the diagonal. There's a lot of things you could do. Like if you cube this, and this one's a much easier matrix to work with, you just cube this one and then multiply it by Q inverse and Q, and you could find A cubed. So similar matrices are important, but we're going to look at a particular type of similar matrix, and that's when the matrix A is similar to a diagonal matrix. So the matrix A is diagonalizable if it's similar to a diagonal matrix D. Okay, there's a couple ways you can write this. You can say that A is equal to Q inverse DQ, where Q is invertible. I actually prefer this because it looks just like similar matrices, but your book actually moves these matrices over to the left. So what your book does is it writes it as, well, notice that you can say that this is Q inverse is equal to D. If I multiply this, the right side, by Q, so if I put a Q here, a Q here, those will cancel. And if I put a Q inverse here, that'll cancel. So it's the same thing as saying that QA Q inverse is equal to D. And in the book, they actually like to use the matrix X. And you can see that if we call X Q inverse, then we have X inverse here. So what I'm saying is, if X is equal to Q inverse, this is the same thing as X inverse A X is equal to D. So this is how they present it in your textbook. They actually solve for the diagonal matrix, and they say A is similar to D, or A is diagonalizable if you have this property. But again, you could leave it like A is equal to Q inverse DQ, or in the case when we involve X, A is equal to X, X dx inverse. Now we're going to talk about some properties of a diagonalizable matrix. So let me erase this so you can just see the part I want you to look at. You don't have all this extra stuff. If you have that X inverse AX is equal to D, a diagonalizable matrix A, you have this property. Well, one thing we can do is we can move this X inverse right here. So we multiply the left and the right by X, and we get that A times X is equal to X times D. Well, X is an invertible matrix, and we're going to label the columns of X as X1 through Xn. So these are columns. And since D is a diagonal matrix, we can label the diagonal entries like this, D1 through Dn, and everything else is 0. And if we want to multiply A times X, and we get X times D, we can actually write this out. We see that A times X is equal to X times D, where X is is partitioned into the columns. And here I've partitioned X in the columns again, and then I have my diagonal matrix. Now you have to remember something you can do when you multiply matrices. You can see that we can distribute this A into this matrix, and that's the same as distributing this D, these D's, into this matrix. And we get that A times Xi is equal to Di Xi. So let's just review real quick what we've done. We've broken a matrix A that is invertible. Call it, this is an invertible matrix. We've broken it up into its columns. And by breaking it up into its columns, we can see that if we multiply by A and then by this matrix D on the back, we get that A times Xi is equal to Di Xi. So the columns are eigenvectors. Because it has the property of an eigenvector. A times this vector is equal to a scalar times the vector. And because the matrix is invertible, remember that the matrix is row equivalent to the identity. So since X is invertible, that means it's row equivalent to the identity matrix. And what does that mean? That means you can get X into reduced row echelon form, and when you do that, it's going to just have a bunch of ones on the pivots. In every single column, you'll have a 1. You'll have n columns if this is a n by n matrix. That tells us that the column space of X is Cn. So each one of those columns is linearly independent from the other columns. Because X is invertible, its columns are linearly independent. Because if you remember, if you try to find the column space, you would have a 1 in every single column, and they would be linearly independent. And because we have this property that A times Xi is Di Xi, these columns are eigenvectors. So what we get is, if we have a diagonalizable matrix, then there exists n linearly independent eigenvectors, and they make up this matrix X. So let's summarize this and talk about some facts. So the first fact is, if we have a diagonalizable matrix, then the columns of X are eigenvectors. We just showed that. And the diagonal elements of D are the corresponding eigenvalues. And we saw that. We saw that each one of these, let me scroll back up. When we let X equal this and D equal this, when we had A times X is equal to X times D, that's the definition of it being diagonalizable. Remember that we got this property here. So we can see that the D's were eigenvalues and the Xi's were corresponding eigenvectors. Scroll back down. So that's the first fact. The second fact is that this matrix X is not unique. Why is it not unique? Well, if you have an eigenvector, let's say X is equal to x1, x2, and so on. Well, if you multiply one of these eigenvalues by a scalar, let's say you put a 5 here, well, you know that A times x1 is equal to something, some di, so d1 times x1. Well, A times 5x1 is also going to be 5, it's also going to be di x1, which is equal to d1 times 5x1. So 5x1 is also an eigenvector, and so we could put that here. That would be an eigenvector in the eigenspace corresponding to this eigenvalue d1. You could also reorder these. You could put x2 here and x1 here, and all that would mean is that you change on the diagonal, you had a d1 and a d2 here. Well, if you switch them, you just need to switch these two eigenvalues. So you put a d2 and a d1 here if you switch x1 and x2. So x is not unique, and d is not unique either. You can switch the eigenvalues. And if you just multiply by a scalar, then d stays the same. Now, if A has indistinct eigenvalues, then we get that A is diagonalizable.